Then we can put all this together. This is when it gets interesting. Okay, so here are some, that's just putting everything together. You can write all that down if you want. Okay, let's talk about phase diagrams. You do have a question on test 3 about phase diagrams. So another way to imagine these circuit elements, our voltage and our current, is imagine this, we call this a phasor, just rotating around. And what we're measuring here is, say, the x component of that. Well, then here I would have, when my phasor is pointing here, I would have positive voltage. When my phasor is pointing here, I would have negative voltage. So these things are rotating around. In a circuit that only has a resistor, these two are in phase. So these two, the current phasor and the voltage phasor, will always point in the same direction. They're in phase. When we only have a capacitor, the current is ahead of the voltage by 90 degrees. So these things rotate around. Imagine this whole right angle here just rotating around together. These two are stuck at this angle. So the current's always ahead of the voltage. Here, when we only have an inductor, the current's always behind the voltage. And this whole thing is rotating around. Okay, that's just putting everything together. Okay, here's all three together. We have a capacitor, a resistor, and an inductor, an LRC circuit. So we have a charged capacitor and we just let it uncharge. The current's going to try to flow through this resistor. This inductor is going to try to stop that sudden change, which is going to create a back EMF, which is then going to charge the other side of the capacitor. So instead of, if we take out this inductor, this thing would just discharge slowly over time. We did RC circuits back before, back when we were talking about direct current circuits. Because we have this inductor in here, we're going to end up charging the other side of the capacitor, which will then discharge going the other way. So we'll start with current flowing this way, and then it will flow back, and then this way, and then back. Now, because we have a resistor in the circuit, we're going to lose power over time. We're dissipating our energy through heat. We end up with a charge that follows this formula. Now, we could balance all this out. We put a voltage source in here. We could balance all this out at a very particular frequency here. We call this the resonant frequency. We're going to need this in a minute. I'm going to write this down. I'm going to show you where this comes from. I really hate how your book covers all this material. Okay, in an LRC circuit, this is everything put together. This is called the impedance. Okay, so the impedance is everything put together. It has units of ohms. This is our Ohm's law complete with everything in it for an AC circuit. VP equals IPZ. So if I have a resistor, a capacitor, and an inductor, I have an LRC circuit. Then the impedance measures the total resistance of that entire circuit. Notice that it depends on the difference of these two. It doesn't matter which one you put first here because we're going to square that difference. Well, when would this impedance reach a minimum? What would be the lowest total resistance? That would be when this chunk here equals 0. That would be, if this is the lowest, we're not playing with the voltage, we have a voltage source. If I minimize Z, then I maximize I. So minimum Z, which corresponds to maximum I, is when XL equals XC. When my capacitive reactance equals my inductive reactance. And so that was omega L equals 1 over omega C. And now if we solve this and figure out what frequency will satisfy that equation, we get this. And we call that the resonant frequency. So if we can balance everything out in our circuit just perfectly, so I have some voltage, I can either change my voltage, pick the right oscillation frequency, the right omega to make this thing balance out, or maybe I can adjust either my inductor or my capacitor, adjust L or C. I can adjust C by changing the width in between my plates. That will change C. With an inductor, remember in the real world for inductors, we don't just have a loop, we also have a bar that we can put inside them. If I can change how much of that bar is inside that coil, I change the inductance, I change L. So we have 3 different ways of adjusting our circuit, changing omega or changing L or C. And typically what we do is we change L. We change the bar that's going through this inductor, or we change the separation plates or distance between these plates. Until we do, we change that until we happen to hit upon the frequency that satisfies this, and we call that resonance. And you do this every day when you're driving to work. This is how your radio adjusts to different stations. This is how you tune in to a radio station. You're adjusting the circuit. It's all digital now, but back in the day it was physical. You physically adjusted pieces until you hit this resonant frequency and you maximize your signal to tune into a radio station. Okay, so here you can see at different frequencies, we get different currents. At this omega, this resonant frequency, we maximize our current. Okay, so what would happen then to a phasor diagram? What would a phasor diagram, what we were looking at, is going to be a test question. Up here, well, a phasor diagram, we want V and I, they would be in phase because these two pieces are canceling out, the L, chi L and chi C. So our phasor diagram would be when these two chunks here are canceling out and V and I are in phase. Okay, then you have a test question. I think it's the last question on the test, or it's near the end, that talks about doubling your resonant frequency. It's a long, complicated problem. I want to give you some hints on it. So here's your impedance. Here's V equals IZ. We want to know what happens when we double the angular frequency. So my suggestion to you is, on that problem, here's a hint, use this formula to solve for omega naught. Get that as a number. You're given L and C, so you can do this. Then using these two formulas for chi L and chi C, plug in that new omega that you got back into here, and then you can solve for, I forget whether it asks for I or V, but you can solve for the one you're looking